Let's see, let's change this. 4 L. And change this. This is our lab number 2, isn't it? 2 by the same name.
Got one quick question on that last slide. You said the data for the boric acid, so it's like the roller or whatever, line, the graph, goes like that, and then LA is supposed to be a straight line and it evens out.
Oh,
The way you graph it,
yeah, when you graph it,
LA was gonna be like hyperbola, and then LA and BA was gonna be the straight line, and then it evens out and they're in.
yeah, this is temperature, this is time,
Yeah.
seconds, this is temperature in degrees C. And the first one, it's going to come down like this, sort of, and then it's going to gradually change like that, and then flatten out.
Yeah.
And then the second one should be in this neighborhood, right? But it's going to go, actually, it may be a little different, might be a little gentler slope. Let's do that.
Yeah, it's way this slow.
But it's going to go past this one. And then it's going to level out. Now, the usually this is going to be your melting point right here, where it settles down.
Mm-hmm.
But if you have trouble, the problem with these amorphous solids, especially these organic acids that we're using, they don't have a very well-defined melting point. In other words, you start to see a little cloudy and then maybe some bigger crystals. And if it were inorganic, the melting point, it would go like that, like that. Just a straight break. So if that's the case and it gets a little squirrely in here, the way that's suggested in that video is that you draw a best fit line for this straight, wherever this is straight, and you throw out the curved part. Draw that one out here like that. And then you take this straight one like this, throw out its curve, and this somewhere in here, if it's different, right, it's going to give you a temperature over here. And the same thing for this one, it'll be over here somewhere. That way you can get around that gradual change. But I've done this experiment. My classes have done this experiment for several semesters, and it works okay if you just use, where it finally settles down, use that temperature. But I still want you to graph it. And then, of course, this would be delta T. All right. So let's see, do we have any pre-lab questions in here? Yeah, we do. All right, well, let's start with the overall concept. What are we trying to accomplish? We're trying to write the rate law for a reaction in which we have two components. Right? We have the blue #1 dye. Right? I used to have blue and red. So if we had a big enough class, then we could have 1 or 2 groups doing red and 1 or 2 groups doing blue. But I find it's easier to grade too if you're all doing the same dye. So we're just going to do blue. And this one is to the N power. That's its order. And then we have the bleach, which is sodium hypochlorite. Right. That will be the model for our rate law. We need to find out this value, that value, and this value. Now, since you're determining the order for the blue, it's going to be a whole number, 0, 1, or 2. But when we get down to figuring out what the N is for the sodium hypochlorite, that could be any fraction. Okay, just a word of warning. And then once you find out what this one is and what that one is, then you just take any value in there, plug it in here for that one, and what's the rate at that point, and solve the K. Okay, but before we do that, let's see, we're going to have 2 experiments. Experiment 1 and experiment 2. And for this one, we are using absorbance from a spectrophotometer as our measure of concentration for the blue dye. We're not going to have a molar value for that. We're just going to use absorbance. And absorbance, well, let's go ahead and do it. Absorbance here versus concentration here. Absorbance is linear with respect to concentration. So as the absorbance increases, the concentration increases in your little cuvette. Or for our case, as the concentration decreases, as bleaches out the blue, then it loses the chromophore that absorbs the light and gives you the maximum absorbance at that particular wavelength, which is 630 nanometers. So they're directly proportional, absorbance and concentration. That's why we can use absorbance as a measure of concentration, because of that fact. And this is due to the Beer-Lambert law, which is concentration is equal to, I usually write it ABC. This is absorbance, right? This is path length, and this is actually I don't guess it really matters. Absorbance, path length, and absorptivity. And that is characteristic of, in our case, the blue dye. And each absorber of any experiment has a different absorptivity. But since it's the same, no matter what the concentration is, this is constant. Right? So the variability here is between the path length and the absorbance. And we're going to keep the path length at 10 millimeters or 1 centimeter. So those little cuvettes are exactly 1 centimeter in path length. The light shines through them, goes through that path length. So this one is going to vary with this. That's Beer-Lambert law. Okay. When we go from experiment 1 to experiment 2, what changes? Okay. This concentration here is the same for both of them. Right. But this concentration is, let's see, let's make it bleach. Bleach 1, and then the bleach, this is bleach 1/2. So we're going to change the concentration of this bleach from whatever the strength is to start with to 1/2. So if you determine the concentration of this one, all you got to do now is just take half of it, and that's for the second one. And we have to do that molarity. And these questions should help us get there. So we're going to use exactly the same amount of blue dye in each reaction vessel each time we do the experiment. But for this one, we're going to have maybe X milliliters of bleach in this one. We're going to have 1/2 X milliliters in this one. But there's this quirky thing about this one, since it's an ionic compound, it dissociates partially. So what we need is to match the ionic strength of this solution and that solution, because these chromophores, those color absorbers, are very sensitive to ionic strength in solution. So we balance it by, instead of this oxygen, now we make up the difference with sodium chloride. Okay. Right. It doesn't have that bleaching quality. It just balances the ionic strength. So we need to know what concentration of this do we need so that we can add the same concentration. So in the pre-lab question 1, pre-lab number 1, we're looking at a container of household bleach has 5% sodium hypochlorite by weight. If the density of this bleach, oh, there's a typo. Density of this bleach is 1.08 grams per mil. Calculate the molarity of this solution. All right. So we're told that the concentration is 5% by mass. Mass, mass. What does that mean? That means 5 grams of sodium hypochlorite for every 100 grams of solution. That's what that means. Okay. We're also told the density. Why do we need the density? Because this has no volume in it. If we're going to calculate molarity, we've got to get volume in there somehow. So what we need is to change grams of solution into milliliters of solution. Right, so 1.08 grams of solution per milliliter of solution would be our conversion factor. 1.08 grams of solution per 1 milliliter of solution. Okay. So that changes, that gets the volume factor in the denominator where it needs to be. So we've canceled this, we've canceled that. Now we need to get moles. Well, and we need liters. Right? So we might as well go ahead and do liters. Right? 10 to the third milliliters of solution is 1 liter. So now this cancels that. Now we have liters in the denominator. We need moles in the numerator. So we got 5 grams. What do we need? Grams per mole. So how many grams per mole is sodium hypochlorite? Well, it doesn't say. So we got to calculate it. Where do we go with that? Right over here. Sodium is 23. Oxygen is 16. And chlorine is 35.45. So that's 74.45. 74.45 grams. Okay, so that gets rid of grams here. Now we have moles per liter. That's the thinking part. Rest is number crunching. Let's say 5 enter, 100 divide, 1.08 times 1,000 times 10, 74.45 divide. So that's 0.725 molar sodium hypochlorite. Okay. So that would be, if we're going to replace the sodium hypochlorite with sodium chloride for the half strength, that would be the molarity of the sodium chloride that we would need. There's just one problem. The bleach we're using is not 5%, it's 6%. So you got to calculate a new concentration for the 6% to find out what this is. Fortunately, I've already made the sodium chloride solutions for you. But if the report asks for that calculation, you got to do it. Okay, so this is pre-lab number 1. Let's see. Oh, number 2. How many grams per liter of sodium chloride would be needed to make that? Okay, so number 2 takes from this place 0.725 moles, and we want the same molarity. So now it's going to be moles of sodium chloride per liter, right? Per liter. Yeah, per liter. So how many grams would that be? This is a one-step conversion. We just need grams per liter. So the moles on the bottom, grams on the top. So what would a molar mass of sodium chloride be? Well, sodium chloride is missing that oxygen, right? So we just take 7445 and subtract the oxygen, 16. 5845. Times 0.725. See. 0.725. 5845. So this is 42.4 grams of sodium chloride per liter. Now I didn't make up a whole liter. I think I maybe made 500 milliliters. So we just need half that because 500 mils is half a liter. But that answers the question. That's number 2. Okay. Number 3 is not related to these, so I can erase them. We can pick up with number 3. This is unit conversion time, isn't it? Way back in chapter 1 and 2. Yeah. All right. So number 3 says, what's the percent of sodium hypochlorite by weight for a liter of bleach that is 0.8 molar sodium hypochlorite and has a density of 1.09? Right, so we're starting off with 0.8 molar sodium hypochlorite. 0.8 moles per liter. And we want percent by mass. Right? So let's get this into how many grams does that represent per liter? Did you write the number down? What was the molar mass? 7445 was it?
7445.
Okay. Right. So that gets rid of moles, and that's grams per liter. But we need grams per grams. So we got to convert this. Actually, we need that in milliliters first. Right, liters, milliliters, and then third. Why? Because the density is in grams per milliliter. 1.09. Right, there we go. So that's grams of sodium chloride per gram of solution, but we need 100 grams. So to make it percent, we just multiply by 100. Okay, that's the thinking part. It's like whenever you calculate percent, you put something divided by something times 100. That's the same thing we're doing here. So 0.8 times 7445 divided by 1,000 divided by 1.09 and then times 100 is 5.46 percent mass. All right. That's 3. Okay. Let's see. There's some background information there. Preparation for the experiment. First thing you have to do is find out how much bleach do I need to add to get to decolor over a span of what, 2 minutes? I think it's 2 minutes, or it's 3 minutes. 3 minutes. All right, so you're going to add so many drops of bleach into 5 milliliters of the blue dye. And you have 3 tubes. One is water, and the other 2 are blue dye, exactly 5 milliliters. And then you add so many drops of bleach. And you take that little pipette that you're using and guard it with your life. Because drops from that pipette are not the same as drops from another pipette. And you need to take that pipette and determine another value using it. So that pipette, you're going to need what? Number of drops of 6% sodium hypochlorite in 5 milliliters of blue number 1 solution. I've already made the solution. So if it says, what does it say, 2 drops per 50 mils or 1 drop per 50 mils, I've already made the solution. So you can skip that step. So the number of drops in order to decolor in 3 minutes or less than 3 minutes. Okay, by just visual observation. And then you need to take that same pipette and find out the mass of bleach per, and pick a number, 30 drops, 40 drops, 50 drops. Just for argument's sake, let's say 30 drops. So you get a little polystyrene cup and put it on your balance and zero it. And then take that same pipette and put 30 drops in it. And that's the mass of 30 drops. That way, let's see, we can avoid, let's see, I was checking something here for a second. Well, we know the density. We know the density of our bleach is right here. We're going to use this one. 1.09 grams per mil is going to be the density of our bleach for any subsequent calculations. But those, you need to know that one, then that one. Now that you know how many drops in 5 milliliters, you got to prorate it because the cuvettes only hold 3 milliliters. Right? So however many drops you get here, you need 3/5 of the number of drops. And that's per cuvette. Now, if we were using one of those old spec 20s with the round tubes, you ever seen one of those? Pop the top, drop your tube in. Those will hold 5 mils. You just use that. But with these new ones, we've got the square cuvettes, and they only hold 3 milliliters. So however many milliliters you find here, take 1/3, 3/5 of it, you do this. Now, if it comes out to a fractional number, just make the call. You know, do you use 2 drops, 3 drops? Well, if it takes, I don't know, let's just argument's sake, it takes 30 drops, right? Then 3/5 of that would be 90 divided by 5. That gives an even number. Yeah, 18. So 18 drops would be what you would use to give you the same concentration. Now, the concentration of the bleach that you put in that solution, you're going to determine the concentration of the bleach full strength, but then you're going to dilute it, right, in that 3 milliliters. So you've got to recalculate the concentration of the bleach for that 3 milliliters. Okay. And that comes afterwards. Let's see. All right, then we're going to, let me erase this. We're going to do 2 sets of timed absorbance measurements. Experiment 1. This one here. Like that, it would need it. 2 sets of timed experiments. And let's see, is it every 10 seconds? Yeah, every 10 seconds. So you're gonna have, and I've already got it on the board in there. I did it yesterday afternoon. You're gonna, for experiment 1, it's full strength bleach. And experiment 2 is half strength. So you're gonna have time here, time 0, and then you're gonna have absorbance. And these spectrophotometers will read out absorbance in 3 decimal places. One thing I didn't say about Beer's law is it's only linear within a certain range. If you get outside that range, if you try to extrapolate, then it tends to do one of these and one of those. And so hopefully we're going to stay in that linear range. And you'll know right off when you plot the data, you'll know if you're in the linear range. And then every 10 seconds. And just like before, don't stop your watch. Just read it every 10 seconds. And you get a value for A. And this is going to be decreasing. Right? So once you get all this data for this one and for this one, what do you do with it? Well, you got to find out what's the order of the blue dye. And you can do that with well, you should do it with both of them just to be sure. So you plot A, you also do a transformation, natural log of A. And if you Excel will do that for you. And then 1 over A. And this is absorbance. So I don't put square brackets around it because this is absorbance. And you get these number sets. And you plot these two, you get a graph. These two, get a graph. Plot these two, get a graph. And that tells you which one's the straight line. Tells you the order of blue. That's the easy part. Let's see. I'll cover that here. And then I forgot to cross this red number 40 out. Here, you don't need the red, because you're not going to do that. Okay. Post lab questions. Okay, there's a page on here for how to calculate the molarity of the bleach. And let me check something. Yeah, we got a few more minutes. Because there are 2 ways to do it. And I think just determining the mass of, say, 30 drops or 50 drops, it doesn't matter really. You just need to know the mass volume relationship. Let's see. Years or years. Keep going. Here. That one. It's this one. Yeah, it's this one. Okay, if you know this page that's in your method for calculating the molarity of the bleach, we're going to modify it just a little bit. So if you find that your bleach, let's go back to that. If your bleach weighs, I don't know, 2 grams or 50 drops. Well, if you use the density, which is grams per milliliter, 1.09 per milliliter, then that means you have so many milliliters per drop, right? Because we cancel the grams. And if you know milliliters per drop, and you know how many drops you put in your, what do we say, 18? Then 18 times that value is per drop. Then you know the volume of bleach that you added to the 3 milliliter cuvette. And the total volume then would be, in this case, would be 3 milliliters plus whatever that is. Okay. And then once you know the volume that's in your cuvette, then you can use that as a dilution factor for the full strength bleach. Let's see. Yeah, beyond that point, when you get past this right here, when you get past step 2, past step 3, milliliters per drop, number 4 says milliliters per drop. And how many drops gives you that many milliliters of bleach added to 3 milliliters, and the total would be, then you have so many moles per drop. That's another one that we have to calculate. How many moles of bleach are added per drop? Well, you need volume of your drop. Right? Because if the molarity of your bleach is what? What's the molarity of your bleach? It's 6%. We didn't do that calculation, did we? We did the 5%. 6 grams of sodium hypochlorite per 100 grams of solution. So we just take this one and you want to convert that to milliliters. So grams per milliliter, 1.09 grams per milliliter. Okay. And then we convert this to liters. Right, then we convert this to moles. And that was 74.45, I think. Bleach. Yeah. And that'll give you the molarity of the undiluted bleach. That's grams per milliliter. Excuse me. That's moles per liter. So moles per liter of sodium hypochlorite. Okay. If you know the moles per liter, then you can calculate the moles per milliliter, the moles per drop. It's just another unit conversion. Once you know the moles per drop, and you know the milliliters per drop here, then you can go to step 4 and 5 and calculate the molarity of sodium hypochlorite. Okay. Maybe instead of going through the rest of it, that's probably enough for right now. Right? We'll get the numbers and then we can work with real numbers. Yeah. Because it's probably just becoming a blur at this point. It is. But you got the basic concept of what we're trying to achieve, how to get good numbers. And what you want to do is, I will say this, at the beginning of each experiment, in the few minutes remaining, you've got your spectrophotometer, and then there's a lid up here, and depending on which one you're using, and there's a holder down here, and it's got a light path here. So the light's going through here and coming out here to the detector. and this is the source. So you have to be sure that your cuvette is optically clean on the surfaces that are being exposed to the light. Right, so that's why wearing gloves is a good idea. Won't put fingerprints on your cuvette. And then use a Chem wipe and just mark it down, because you can see fingerprints pretty easy. So when you put your cuvette in here, you just need to be sure that it's seated in the bottom and you have it turned right. So these cuvettes are frosted on two sides, and those are the sides that go parallel to the light, so that you get the clear ones perpendicular to the light. So the frosted side is going to be this side and the other side. So you need to zero your spectrometer before you start. And you do that with water. That's the best way. Just take that same cuvette and fill it with water, stick it in there and zero it. And right before you get started, just take that cuvette out and empty it and sling it real good. That it is hydrophobic, so it's going to let loose all the water. And then you put your solution in here, your blue dye. And then, right before you get ready to start, you add the bleach. So many drops, however many, 18, say for argument's sake, 18 drops in there. And it needs to be mixed. So when you put the 18 drops in there, we'll have a glass rod. And you take the glass rod and just dip it 2 or 3 times, and that'll mix it good.
So the gently swirl it.
Yeah, it's kind of hard to do with a square cuvette.
Yeah.
So we're going to use it. Or you could get a separate pipette and just stick the pipette in there and suck up some and squirt it out a couple of times. And that makes it, either way, it works fine. And then, as quick as you can, start reading. That's your time zero. Read your value, and then start reading. And you want to read, I think the method calls for till the absorbance gets down to what? To some value. 0.1. When the absorbance is below 0.1, you can stop. I like to go a little more, because you can always throw data away, but you can't create it. And so if you get extra numbers at the end, that's fine. What's going to happen is below 0.1, I think then the curve starts to flatten out. Okay, any questions? All right, so this is Thursday. We have an exam on Tuesday.